Of course, it is time for what we've all been waiting for. We want to try the Tillamook. Let's see if it posts. Fingers crossed. Ready? Hello everyone and welcome to today's video. We are going to finally try the Tillamook, which is sleeping in this cardboard box. There it is. So this chip we had already on the channel. It had some bent pins, which I hopefully fixed. So we'll keep this safe for now, because first we need to address something on the board that we are going to use. This is the ASUS P5A-B. This board I restored last week. So today we are trying to finalize whatever needs to be done on this board, and then we'll try the Tillamook. So what's wrong with it? Because the board is working now. Well, the problem is the I/O voltage for the Tillamook. The Tillamook has a split voltage rail. We have 2 volts on the core and we need 2.5 volts on the I/O pins. The problem is no socket 7 or super socket 7 board that I know of is capable of changing the I/O voltage for the CPU to 2.5 volts. However, many people are running the Tillamook on regular socket 7 boards and the CPU seems to be fine. For how long? I don't know, so there's always a risk. But the problem with this super socket 7 board is that it doesn't send 3.3 volts, it actually sends 3.5 volts. And this is even outlined in the manual. After some research, I found out that this was done because of the ALI chipset, the Aladdin 5. This chip was notoriously unstable at 100 megahertz, even though it's written right here on the packaging. And that is why many manufacturers bumped up the voltage. And there is a jumper block up here right next to the AT power connector, which can be used to set a different voltage from the 3.5 volts we have right now. Unfortunately, we can only go up. And I want to change that. For that, we have to figure out how the voltage regulator circuit here works in the top corner. You may remember that I replaced a resistor here, and this was actually connected to the feedback pin of this PWM controller. Let's also quickly check our resistor that's here on the top. So this is a 10 kilo ohm resistor, which is connected to the feedback pin. Let's see what we get on one side. We get 3.5 volts. This is the output of our regulator. And on the other side of this resistor, we're getting 1.26 or 1.27. Remember this number because it will appear again later in the video. I'm still scratching my head over this Tillamook chip. Seeing it on a socket 7 adapter makes me wonder, was this a legit aftermarket product or just a clever way to move mobile chips to the desktop market? Either way, it is a perfect example of why custom PCBs are the backbone of so many projects. Honestly, if these chips weren't so rare, I'd be ordering a batch of my own adapter designs right now. And when I do, I'm headed straight to PCBWay. I've used them for my memory expansion boards, which you can find on their shared project space, and the quality was always spot on. But the cool part is that you don't even have to be a PCB designer to use them. If you've got an idea but stuck at routing traces, their expert layout service can do the heavy lifting for you. Once your design is ready, or if you found a project online, just upload the Gerber files, pick your specs, and the boards are with you in no time. And if you don't feel like hand soldering hundreds of tiny SMD components, have a look at their assembly service and save yourself hours of handling a soldering iron. They also do CNC machining and 3D printing if your project needs a custom housing. It's basically a one-stop shop for bringing your projects to life. All you need to do is head over to PCBWay.com and explore the world of possibilities. Links are in the video description. And now let's have a closer look at this voltage regulator circuit. Okay, so then let's probe around our circuit a little bit. Here we replaced some components. This was in my last video. So we replaced this resistor and this capacitor. This resistor just continues here and goes to pin number 5 on this HIP6013CB. This is a controller chip which switches this guy on and off. So this is the 76121S. It's some sort of a MOSFET probably. Switching on, switching off, depending on what our HIP chip is gonna tell it. So basically this is a switching power supply because it switches the MOSFET on and off. But now let's have a look at our VIO section here. There are 6 pins. Let me just remove the jumper here. Actually, let's remove it completely. So there are 6 pins. And you can see there are resistors. The first thing what we want to do is we want to see where they go. So one side we can see is going into vias and disappears. So let me put one probe on ground and let's probe each of them. First one. So this one connects to ground. Second one also to ground, ground, ground. So all of these sides of these resistors connect to ground. The other side connects to our jumper block. Here's our jumper block. So let's try each resistor again. So we see there's a trace going, and where does it go? This one. So this left resistor goes to this pin. The next one probably goes to this one. Yes. Then we have this one, which goes to right top. And this one here most likely goes to our right bottom. And no other pin. Yes, that's correct. So, and what are the middle pins? First of all, let's see if these 2 pins in the middle are connected to each other. Yes, they are. So now you have to trust me that I'll remain with this probe on the middle pin. And let's connect to our feedback pin. This is pin number 5. So here's 1, 2, 3, 4, 5. Aha. So we go directly to our feedback pin, which also connects to our 10 kilo ohm resistor here. The other side we said goes to our output of our MOSFET. So we have the output voltage, the one that goes to our CPU, goes also in here through this resistor, and then we can add one of these resistors that are here into the circuit. So we're basically building a voltage divider by closing these bridges. So then let's measure these resistances here just to understand what we are dealing with. So this one is 5 kilo ohms, 5.5, 5.25, and the last one is 4.65. Now let's do some math. Okay, we do simple math. Anyway, for completeness, I have added some formulas here. Let's just discuss quickly this reference voltage. This is specified in the HIP 6013 datasheet. So it has a reference voltage of 1.27 volts. It's the internal reference, and that is why this value appears here as well. And this is also what we measured on the feedback pin. So yeah, this is an important voltage, and that is why it is also part of this formula. So this formula is being applied here. We see VR1, the very left one, we measured 5 kilo ohms. Then we had 5.5, 5.25, and 4.65. So these are our resistor values. The R131, this one was 10 kilo ohms. And here is the calculated value. And this is basically this formula that is here. So let's say I want to get our 3.5 volts down to 3.3 volts, what I was expecting initially on that board. So we can see that the lower the resistance here is, the higher the voltage gets. So this is our lowest resistance on one of these VR resistors, and this is 4 volts. So if I want to get this to 3.3 volts, I think I have to go even higher than 5.5. So let's try 6,000, so 6 kilo ohms. Okay, then we get 3.4. Okay, let's add another 500 ohms. And here we are now at about 3.3 volts, 3.22. So yeah, definitely we're getting lower. The problem is I don't want to change these resistors because they're very difficult to get to. Maybe we can just change our R131. This one I already replaced. It's easy to access. So let's say 12 kilo ohms and our voltage will get higher. So we have to go in the other direction. Let's try 8,000. And this is actually almost this what I want to achieve. So let's see if we can get 7,500. Perfect. Perfect. This is what we want. We want this on our 3.5 volt pin. This is for the Tillamook. I'm not saying this is something that you should do with your board. This is I want to do with my Tillamook. So my 3.5 volts becomes half a volt lower. Okay, so that means we just have to replace our 10 kilo ohm resistor with a 7.5 kilo ohm resistor. And the nice part is that our 4 volts become exactly 3.3 volts. But I want to try this with a variable resistor. I basically want to use a potentiometer that I can adjust the voltage on. So I have a 10 kilo ohm potentiometer here. Now, unfortunately, this potentiometer starts at 9.5 kilo ohms. So we'll already start with a little bit lower resistance. So we get 3.4. And I will take off the beeper now. We get 3.4. Now let me move the potentiometer. Let's see what we get. You see, we can go lower. 3.3 volts. 3.2. 3.1. 3 volts. This is what I want to achieve. So our potentiometer is now set to produce 3 volts on our ASUS P5A-B on the I/O pins and also on the SD memory, on the chipset, on the AGP slot, and so on. Okay, the first thing I want to do now is I want to figure out what is the resistance of our potentiometer. So for this, I have to take off this one parallel resistor again. Huh. Look at that. Exactly 7.5. And of course, it is super difficult to find a 7.5 kilo ohm resistor, but we can use two 15 kilo ohm resistors here and here and just stack them on top of each other. Then we should also get 7.5 kilo ohms. So let's try this. Here is one of them. And here is the other one. Okay. And here is the second resistor. This one we just piggyback on top of the other one. Okay. And what do we get? There you go. And we get exactly 7.5 kilo ohms. This is what we need. Okay, so next step is to get, so this is 3.5 volts. This should be exactly 3 volts. And we're getting 3 volts. Let's try our next configuration and get 3.1 volts into the CPU. There you go. So 3.1 is here. 3.1 works. 3.2. Yeah. Now let's just try the last one. This should be 3.3. Okay, so here is our VRM mod for the CPU, but we are running the first one at 3 volts. So that is what we are going to try. Okay, board is configured. We have 3 volts on the I/O pins and we have 2 volts on the core. Now, of course, it is time for what we've all been waiting for. We want to try the Tillamook. no sign of life. What a shame. So the only thing I can try now is we move this voltage 1 up, but I highly doubt anything is happening here. No. This chip is not working on this board. That's really sad. Well, not every project is going to be a success, but we have a nice motherboard now with a new socket, with a modified VRM that no longer puts too much voltage into our components. Unfortunately, the Tillamook doesn't want to work. Okay, of course we're not gonna give up because, well, there is something else we can try, and I really have no idea where this is going. I am just going all out now trying to get this chip to work. So there are some mods that sometimes are required and sometimes they are not required. It depends on the board. And we know that Peter was able to run a Tillamook on this board. Now he had a modified socket 7 CPU. Maybe they did the mods already in the package. For me, this might not be the case. This is just a PCB and we're just having the pins mapped out. Let's figure out the first mod that is sometimes required on boards, and it's an easy one. There are detection mechanisms on the socket to figure out if this is a dual voltage or a single voltage CPU. So for the motherboard to know if this is a Pentium MMX or any other chip, there are 2 pins that need to be shorted. I'll show it here on the screen. So on this CPU, I know it is, for instance, this pin, the second from the bottom, if you have the notch on the top left, the second on the left row from the bottom should connect to this one. This is ground. So let's measure these 2. I have my multimeter in beep mode. So if I go here and let's measure to this pin here, which I know is ground. Yes, they're grounded. So the Pentium MMX for sure tells the board, hey, I'm a dual voltage CPU. Now let's try a Pentium non-MMX. And here is a Pentium non-MMX, and this is a 3.3 volt CPU. Let's measure here the same pins. So it's this one here, and we're going to this, and it is not connected. So yeah, this chip is signaling something else to the motherboard. Now the question is, what is this chip doing? Of course, if you have then a chip that also in combination to this one signal responds to something else, do I have this signal, then I'll only give another signal that continues the entire process to post. And the motherboard thinks there is no CPU inserted in the socket. And this was an indicator because when I powered on this board and I got the dashes on my postcode analyzer card, the LED remained off as if there is no CPU in the socket. So now the Tillamook is in the system, and I already marked, you see the black dots here. So this is our detect pin, this one, and it should connect somewhere here. This is ground, or I can go here ground. It is not connected to ground. So yeah, maybe this is all we need to do. We need to short these 2 pins with a Tillamook. I'll add a bridge and then we'll try this chip one more time. All I want to achieve today is to see if this Tillamook chip is working. There may be more mods that we have to do to enable level 2 cache, all sorts of things, which, well, I guess if we get this chip to work, we will have another video looking at all the other mods, enabling level 2 cache, enabling the additional multipliers that are maybe not working on certain motherboards. So yeah, it all depends. Okay, not the nicest, but I think this is it. So now we should have a continuous pull to ground from this pin. Yeah, so that's it. Question is this the fix? Okay, smoke test. Let's see if we get postcodes. I'm very nervous now. I hope you're too. I really don't know what's going to happen. Yeah, it's there! It works! Oh. Yeah, so it's detected as a Pentium MMX. Let's have a look at power management. So we are running at 2 volts core and 2.9 volts on our I/O pins. So this was the entire exercise, trying to get our I/O voltage down from 3.5 volts to 2.9 volts. Now we're only overvolting 0.4, which is much better than the 1 volt overvolt. And the chip is actually not getting that warm. I have a heatsink on top of it, so I think we should be fine. That's a pretty cool experience so far. Let's see, we have caches enabled, so... And cache memory 512 kilobytes, so it's written in our system summary up there, so maybe it is there. Yeah, and now it looks like we have a working Tillamook on a Super Socket 7 board. And 512... Yay! So the cache is actually working on this board. The only mod I needed was to short the VCC detect pin. Okay, here you go. So we have 512 kilobytes of level 2 cache detected. Super, super nice. So what I will try now is to set a 3x multiplier, but at 100 megahertz frontside bus. Nope, C0. Might be related to the multiplier. This one at least works. Let's quickly check our voltages. 2 and 2.9. So yeah, this is still good. Let's just go to DOS and let's run some benchmark on this Tillamook. And then maybe in the next video we try to mod this board further to unlock higher multipliers. Anyway, let's have a look at SpeedSys one more time to make sure that, well, it still detects the Tillamook. Yes, so it is still there. Now it's running at 233 megahertz. Unfortunately, I don't seem to be able to push higher frequencies right now on the frontside bus. I'll still experiment a little bit and we'll see what we can achieve. At least the chip is working. So we have 16 kilobytes and 512 is still there. Let's run Quake. Hey. Okay. At least it started. Let's see if it completes. Well, this project definitely cost me a few gray hairs. Yeah, so you can already let me know in the comments what you think about this. And we just kept digging and figure out what has to be done to get this chip working. Let me know in the comments what you think. And yeah, if you want to support the channel, please head over to Patreon or become a member here on YouTube. 16.9 frames per second. Cool. So this chip should behave identical to a Pentium MMX 233 right now at this clock speed. The potential to have 300 megahertz obviously changes the game. And this is all I wanted to have for this video. Okay, thank you so much for your time. Thanks for watching. Leave a comment, like the video and subscribe if you haven't already done so. And thank you PCBWay for sponsoring this video. And I'll say goodbye and I hope I will see you in the next videos. Take care and bye-bye.